Let me tell you another idea. Next idea is an idea in number theory. I saw this idea in BMO round 2. I think BMO round 2 of 3-4 years ago, British Mathematical Olympiad. Also, I saw this idea in AMC 12A 2023. Also, I saw this in one problem of, I think I saw this 14 years ago, this idea. In a book. Uh, it is number theory, and the author is Mariam Mirzakhani. You know Mariam Mirzakhani?
Very famous.
Yes. And I saw this idea. Let me tell you something. In PMO on in AMC 12 2022, I saw this problem. I don't remember A or B. I will tell you. Then I saw again this idea in PMO, and this problem of PMO was exactly same as, I will tell you the problem was what was exactly same as PMO. PMO is for Philippine Mathematical Olympiad national level. PMO national means similar to USOMO or BMO round 2. PMO national level 2023. Okay, and these two problems are exactly same, but here, the ideas are similar. Okay, background. Let me tell you is what. At first, suppose a and b are x squared, and GCD of a and b is 1. What can we conclude?
A not equal to B.
A and b are relatively prime, and product of AB is a perfect square.
Okay.
So try to see what can we conclude about A and B.
Do A and B both have to be 1?
Uh, A and B both have to be 1. For example, let me tell you an example. Suppose, for example, AB is equal to 100 and A and B are relatively prime. Okay? What are the cases for, suppose A and B also are positive integers, okay? Also, it's not important if there are negative integers, both of them should be negative, right?
Yeah.
So we can say without lots of generality, we can consider both of them positive because, for example, if you have, for example, 5, 4, we can consider negative, if negative 5, negative 4, 5, 4, right?
Yeah.
Okay, now for this case that AB is 100, calculate all cases of A and B, okay?
Okay. There's 100 and 425.
Exactly. So look, it is 100, or you can switch, and 425, right? Again, you can switch. So 100 is 10 squared, right? So it means that in first case, A is 1 squared, B is 10 squared, A is 2 squared, B is 5 squared, right?
Right.
So we cannot conclude A and B are 1, right?
So both A and B are perfect squares.
Exactly. A, for example, is x1 squared, B is x2 squared, right?
Yeah.
But if they are not relatively prime, you can't conclude this. For example, here, if they are not relatively prime, you can say A is 2, B is 50, right?
Yeah.
Okay. It is first one. Now, let me tell you another thing. Suppose AB is P times x squared, which P is prime, okay?
Okay.
And GCD of A and B is 1. So in this case, what can we conclude about A and B? Try this one.
So is it that one of them is a perfect square and the other isn't?
One of them is perfect square, and the other one should be what?
The other one is a multiple of 4.
No. Look, for example, x1 squared means you consider from here. X squared, x1 squared. So what is left?
T.
P times?
Uh,
For example, let me tell you an example. Suppose AB is 3 times, for example, 36 squared. Can you tell me, and suppose GCD of A and B is 1, okay? Can you tell me an example for A and B?
1 and 36 square times
Yes, what else?
um
You can say one more example. Try to find
okay.
what is left. Want hint that the other case is what, or wanna keep trying?
Could you give me the hint?
Okay, sure. So 3 times 36 is 4 times 9. 9 squared and 4 squared, right? Agreed?
So 81 and 16.
3 times 9 squared, 3 times 81 and 16, right?
Okay, yeah.
Okay, so one of them x1 squared, the other one is p times what?
P times x2 squared.
Exactly. Okay, so we have these two forms. Understood completely? Okay. Let me tell you one more point, then we will solve the problems. Suppose, for example, we have a and b. A and b, for example, are positive integers. And suppose GCD of a and b is d. Okay, they are not relatively prime. And the remainder is d. They are not necessarily relatively prime. D can be 1 or any other number. Do you agree? Because GCD is a, GCD is what? Greatest common divisor. So a is multiple of d or d is multiple of a?
A equals a prime d.
Exactly.
So
And
d is
b is what?
b prime d.
And can you tell me GCD of a prime b prime is what?
1.
Yes, because if it is greater than 1, then GCD of a and b will be greater than d, right?
Yeah.
This form again is so much important. Let me show this. Okay. Now, if we had, for example, a problem, it says again, a and b are positive integers. And ab is x squared, and GCD of a and b is d. In previous case, we considered only the case that a and b are relatively prime, right?
Yeah.
So in this case, we can say a is a prime d, b is b prime d, and a prime b prime d squared is x squared, right?
Yeah.
So we can conclude a prime b prime is x over d squared, which is, for example, y squared, right?
Yeah.
And GCD of a prime b prime is what?
1.
Now it is previous problem, so we can conclude a prime b prime are what?
A prime b prime are both perfect squares.
Exactly, y1 squared, y2 squared. So we can conclude a and b are what?
A and b.
A prime b prime are y1 squared, y2 squared. A is a prime d, b is b prime d. So a is what?
Uh, d times y1 squared.
Yes, and b?
D times y2 squared.
Exactly. Okay. So, previous problem was a special case. When d is 1, they are perfect square. If d is not 1, a is d times perfect square, b is d times perfect square, right?
Yeah.
And if you write also for this case on, here we can say without loss of generality. Because also a can be p times a perfect square, b a perfect square, right?
Right.
Okay, now for this case also, if a and b are positive integer, and ab is p times x squared, p is prime, and GCD of a and b is d. So can you tell me, we can conclude what? Can you guess?
Um, a prime is going to be
Yes, we can conclude a prime, b prime, then a and b. Can you guess a and b will be what?
will be will a prime be p y1 squared?
A is dy1 squared, b is p times, or d times p times y2 squared. only you should multiply by d, okay? But here I proved this as homework one, try to prove this, but it is similar, okay?
Uh,
Okay, now I told you all four parts. We can consider this one case one, this one was case two, this one case three, when the GCD is D, this one is case four. Okay, let's start. Firstly, we'll be working on AMC, then BMO, then I will tell you again this problem. You can try this as homework. This one is so much harder, but these two problems are easier. So problem of AMC is what? Problem of AMC 12 is this one. Try this problem first on your own, okay?
okay.
Want hint for this problem, or want to keep trying? Okay, sure. Sure.
The D18?
18. Okay, let's check. It says Tn at first. Tn is what? 1 to n is what?
N times n plus 1 over 2.
Exactly. And it says what? The three smallest triangular numbers that are also perfect squares are 1 squared t1, t8, this. What is the sum of the digits of the fourth smallest triangular number that is also a perfect square? So we can consider this one is x squared, right? So then what can we conclude?
N times n plus 1 is 2x squared.
Yes, then we should do what?
So 2 is prime, so by the
GCD of n and n plus 1 is what?
1.
Yes. Do you know how to prove GCD of n and n plus 1 is 1 or not?
Yeah, do d divides n and d divides n plus 1.
Yes, d divides subtraction, so d divides 1, right?
Yeah.
Okay, good job. Now from here we can conclude what?
So one of them without loss of generality.
Oh, here we cannot say lots of gen because one of them is n, one of them n plus 1. Then they are not, the problem is not symmetric. We should consider both cases. Okay?
Okay.
So tell me, first case is what?
N is x1 squared.
Yes, I'm n plus 1 is what?
2x2 squared.
Yes, good job. Case 2 is what?
N is x2, x1, 2x1 squared.
And because we have x1, x2, let's use new variables. 2y1 squared, right?
Yeah.
N plus 1 is what?
Just y2 squared.
Yes, so we should, for each of them, we should find minimum n that satisfies this, right? Or we can work on them simultaneously. So, for example, for this case, what should we do?
That case, I just did like casework on it.
Yes, here we agree we can say n is x1 squared, and so x1 squared plus 1 should be 2x2 squared, right? Agreed?
Yeah.
Because look, n is x1 squared. If you replace here, x1 squared plus 1 is 2x squared, right?
Yeah.
So let's check. 1 squared plus 1 is 2, right? Here, the problem says, for example, n1 works, but we have t1, t8, t49. We should find after that, right?
Yeah.
So we know n is at least what?
1225.
No. Look, 1225 is n times n plus 1 over 2.
40. 40. 50. I mean.
50, yes. Greater than 49, so at least 50, right?
Yeah.
Okay, so we know because n is at least 50, so x1 is at least what in this case?
X1 is at least 7.
8. 8. Because 7 squared is not less greater than equal to 50, right?
Yeah.
Okay, x1 is odd or even?
X1. It's odd, I think.
Yes, because here, even, so this part is even, because we have 1, x1 should be odd, right?
Yeah.
So let's check some cases. First, x1 that we should check is what?
9.
Yes, 9 squared plus 1 is equal to what?
82.
82 is 2 times what?
41.
Yeah, so it's not good because 41 is not perfect square, right? For example, next one, 11 squared plus 1 is what? 122, 2 times 61. It doesn't work, right? And because we want to find a smallest number for n, let's check both of them simultaneously because maybe, for example, one of them we should check a lot of numbers, but in the other case, we can find a smaller number, right?
Yeah.
So next one is what? It is 2y1 squared plus 1. Should be a perfect square, right?
Yeah.
Again, here we can say y2 is odd or even.
Odd.
Odd,
No. Yeah.
yes, because it is even plus 1 odd. And we can say, for example, y2 is at least what?
Y2 is at least 8.
Yes. So if we check, for example, we can check again this part. Y1 is at least what?
Y1 at least the 6.
Uh, what about 5? We can also say 5, right?
5.
Yes, because 2 times 5 squared 25. 2 times 25, 50. So we can start from y1, 5, right?
Yeah.
Okay, so we can say, for example, 2 times 5 squared plus 1 is what?
51.
It's not good. It's not a perfect square, right?
Yeah.
So next one. 2 times 6 squared plus 1 is what?
73.
Yes, 73. It's not a perfect square. Here, look, because n is 2y1 squared, or we can say n plus 1 is y2 squared, we can say 2y1 squared is 72. We've checked up to 72. From here, if we check, n is what? Here, or we can say x1 squared plus 1. Here we've checked what? We checked 11 squared, right? In this case. So we are checking numbers quickly. Let's check next one. 2 times 7 squared plus 1 is what?
99.
99 is not perfect square. 2 times 8 squared plus 1 is what?
1, 2. Mhm.
Yeah, 64. 2 times 64. 128, 129. It doesn't work. Now they reached. They are near to each other. Let's check next one here. Here we should check what number next.
13.
13 squared plus 1, which is what?
170.
Which is what? 2 times?
85.
Not good. Next one, 15 squared plus 1, which is?
226.
Which is 2 times?
113.
Not good. Next one, 17 squared plus 1 is what?
17 squared plus 1. 289.
289 plus 1,
290.
which is 2 times 145, right?
Yeah.
Okay, now let's check some numbers here. 2 times 9 squared plus 1 is what?
163.
Yes, 163. It's not perfect squared. 2 times 10 squared plus 1 is what?
201.
It doesn't work. 2 times 11 squared plus 1 is what?
1243.
11 squared is 121. It's 243. Not perfect square, right?
Yeah.
Okay, so this one is not perfect square. This one is not. Let's check next one. 2 times 12 squared plus 1 is what?
289.
Is it perfect square or not?
Yeah.
Okay, it's perfect square. In this case, n will be what?
7.
n,
And is
this one is 2 times this plus 1. y2 squared. So n is what here?
and is 289
No,
or 288.
288, because n plus 1 is y2 squared. y2 squared is 289, so y2 is 17, or y2 squared is 289 minus 1, 288, right?
Yeah.
The only thing is to check here to not have a smaller, a better answer. So 17 squared, next one. Because here n is x1 squared plus 1. So 17 squared. Do you agree if also 19 squared be good? 19 squared is 361, will be greater than this answer, right?
Right.
So our answer is 288. You can also check that it's a perfect square because t of 288 is 288 times 289 over 2. And you will see it is 144 times 289, which is what a square? 12 times?
12 times.
Yes. And the problem says what? What is the sum of the digits of the fourth smallest triangular number? That is also a perfect square. So we should calculate this, right?
Yeah.
Okay, 12 times 17 squared. Have you calculated this?
Yeah, I think so.
It is what?
Um, Actually, I think I erased it, but let me do it quickly.
Okay, sure.
204.
It's 12 times 17 squared is what? 12 times 17 is 204. This one squared is what then?
It's 41616.
It's 41616, you said? So sum of the digits is what?
18?
Yes. Your answer was this? You said 18 or different?
Yeah, 18.
Uh-huh. Okay. So here in this part, we used the idea, right? In AMC.
Yeah.
Okay. Now let's see how we can apply it in BMO. It is, let me tell you, BMO round 2, 2017-18. BMO round 2, 2017-2018. We will solve this one then. I will tell you problem of PMO and Mariam Rizafani as homework, and then we'll be working on next idea. So here, let me try this problem again first on your own. Okay.
Okay. Could you scroll up for a second to the stuff we did at the beginning?
Okay, sure. Let me go to this part. Is it okay?
Yeah, that's good. Thanks.
Okay.
So I got it to a point where 5m plus 3 and 3m plus 1 are both even perfect squares.
Okay, let's check. Let's try the thing you said. Here, you should memorize this identity in many problems of, for example, AMC. You should know this, but here it was a hint. It says, can you tell me this part is what then?
It was so 2m times 2m plus 1 over 2 squared minus m times m plus 1 over 2 squared.
Yes, or we can say this one whole squared also, right?
Yeah.
Let's call this A. Is this minus what?
Minus m times m plus 1 over 2 squared.
So then we can write it as what?
If you simplify it completely, it becomes m squared times 5m
You
plus 3.
expand these two parts?
Yeah.
Do you agree we can factorize A minus B, A plus B?
Yeah, you could.
And then the product is perfect square, we can use that lemma, right? Because if you expand and then want to factorize, it will be harder, right?
Yeah.
But because it is A squared minus B squared, you can easily say, okay, A minus B, A plus B, right?
Right.
Okay, so it will be what? It will be 2m times 2m plus 1, or we can write 2m times 2m plus 1, plus m times m plus 1 over 2, right?
Yeah.
And what? 2m times 2m plus 1 minus m times m plus 1 over 2. Agreed?
Yeah.
Okay, then it is equal to what? Yeah, we can factor from m.
Yeah.
It will be m times what?
2 times 4m plus 2
Yes.
plus m plus 1 minus 2m minus 1.
No, again, we should factor from m, right?
Okay.
M times what?
2m plus 1 minus m minus 1.
4m plus 2, right?
Yeah.
Minus m minus 1, right? Over
Right.
2. So it will be m squared over 4. Agreed?
Yeah.
Times what? 4m plus m, 5m plus 3.
Yeah.
Times what?
3m plus 1.
It is equal to perfect square, right?
Yeah.
Okay, m is odd or even?
M is
It can be both odd and even, because if it is even, this one is multiple of 4. If it is odd, this one is even, this one is even, right?
yeah.
So, do you
Could you
agree
like move
what? We can move what?
the m squared over 4 to the right?
Exactly, we can say 5m plus 3 times 3m plus 1 is equal to 2x over m whole squared, right? And it should be
Yeah.
integer because here it's integer, right? X squared should be multiple of m. So we can say this one is y squared, right? Now product of two terms equal to y squared, then and we can apply things we had, right?
Yeah.
Want to try on your own or want hint?
I already did this.
Okay, so here in next step we should do what?
Find the GCD of 5m plus 3 and 3m plus 1.
Exactly. Suppose GCD of 5m plus 3 and 3m plus 1 is D. How can we find D?
D divides 5m plus 3. D divides 3m plus 1.
Exactly.
D divides 15m plus 9. And D divides 15m plus 5. So D divides 4 and GCD is 4.
D divides 4. D can be what?
4 or 1.
4 or 1 or?
2.
Exactly. Now, in general, we said when it is this and the It is perfect square. We can conclude what?
5m plus 3 is 4 times like z squared.
Let's write it in terms of d. It is what?
Okay, d like z squared.
Yes. And 3m plus 1 is what?
Uh, d z2 squared maybe.
Yes, z1 squared, for example. Do you agree if d is 1 or 4, then 1 times z squared again is a perfect square, or 4 times z squared is a perfect square, right? Agreed? If it is 1 or 4, then again the product will be a perfect square.
Yes.
So case 1 is 5m plus 3 is y1 squared, 3m plus 1 is y2 squared, right? Case
Yeah.
2 is 5m plus 3 is what? 3m plus 1 is what?
2z.
For example, because we had, see, let's write, for example, 2w1, here is 3. 2w1 squared, 2w2 squared, right?
Yeah.
Okay, we should consider these two cases. If it is 4, it will be case 1, right? Or 1, if d is 1 or 4. If d is
Yeah.
2, it will be case 2. Now we should check these two cases, okay? Want hint for how to check these two cases?
Yeah, that's what I was like stuck on.
Okay. Here, you should reach contradiction, okay? None of them works. How? By considering mods, arithmetic modula, okay? So
Okay.
you should find a good mod to reject case 1 and also case 2. Want more hint or that's enough?
So like set m equal to something odd something.
Not m
Something.
equals. For example, let me check. Let me reject one case for you. Here, I want to focus on this part. Can you guess we should consider mod what for checking this case?
3m.
Exactly. Mod 3. Okay, mod 3 is enough. Mod 3. Left hand side is what?
Uh
3m
2w
plus
squared.
1. 3m plus 1 mod 3 is what?
1.
1. And this one is 2w2 squared. Okay? Can you tell me w2 squared mod 3 can be what? If you check all cases.
I think it's 1, 0 or 1.
Yes, because 0 squared plus minus 1 squared, right? Because mod 3,
Yeah.
2 is minus 1. So if you check, it will be 0 and 1, right? So
Yeah.
2w2 squared can be what?
0 or 2.
So do you agree it's not possible because 2w squared can only be 0 to mod 3, but this one is 1, so that's a contradiction, right?
Could you say that again?
I said 3m plus 1, the remainder when divided by 3 is 1, right?
Yeah.
But if you consider mod 3, this one is 1. This one can only be 0 or 2, so it's not possible
Um,
that these two
okay.
things be equal. Agreed?
Okay. Makes sense.
Now try to reject this case on your own, okay?
Okay.
Let me just check something with you. Have I told you all important ideas of geometry? I don't think so.
Like I think you told me altitudes, bisectors.
For example, let me ask you something like this. AI over ID is what? Have I told you this?
Like B plus zero, I think.
So I told you these things, right?
Yeah, you
And
told me. Yeah, I think
how,
we ended with like a PMO problem.
and for example, how I told you when we have something like this, these lengths are what?
Yeah, the in center and X center.
Have I told you AI? Let me just check. AIA is what?
I think you have, but it's like something
B3 over S
positive.
minus A times cos A over 2. I told you this?
Yeah,
Okay, so I think I told you all properties of. If I told you all properties of altitude, means I told you all of them. Because, for example, have I told you this R is A over 2 sine A?
yeah,
So I told you this. How I told you orthic triangle, when you connect them,
yeah.
it
So
is A cos
we
A,
solved
the side length are these.
we, we solved the AIME problem.
Okay, okay. So great. I just wanted to check. Okay, okay. Keep trying.
Okay, so if you consider mod 5 for 5m plus 3,
Mm-hmm.
uh, y1 squared can be 0, 1, 4 mod 5.
Yeah, 0 plus 1 squared, 0 squared plus minus 2 squared. When we say 0, 1, 2, minus 2 is 3, minus 1, 4, right?
Yeah,
Okay, so, but it should be equal to 5m plus 3, which is congruent to 3 mod 5, right?
yeah,
And it's not possible. So we proved this BMO problem, right?
yeah.
Okay, now let me tell you the problem of PMO National Level 2023. It was this. You can try this one as homework 2. Let me tell you homework 3, the problem from Mariam Mirzakhani book. You will see they are same. Okay, this book, I think I saw the problem 14 years ago, but I think the book is for example, maybe 20 years ago. The problem is what? The problem is this: find all primes p such that 2 to the p minus 1 over p is a perfect square. Prove now that these two problems are equivalent. Means if you prove one of them, the other one will be proved. Okay? Only I don't want to prove one of them, but only prove equivalency between them. Okay? Try.
So you mean like the primes are equal in both of them?
This problem says find all primes p such that this one is a perfect square. This problem says find all primes p such that this one is a perfect square. Okay? I want to say if you know, for example, solution of this, you can easily solve this one.
Oh, okay, yeah.
Find why it's possible.
Could you scroll up again?
Okay, sure. So, you don't need to scroll to use previous idea. Let me tell you something only. Can you tell me the relationship between this and this is what?
Uh, they're both difference of squares.
No, 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 no. For example, if it is t, this one is what in terms of t?
Oh,
Or let me tell you a better thing. If this one is t, this one is what? This fraction is what in terms of t?
t squared.
T squared, it will be 2 to the 2p minus 2. It is what?
4t.
4t. Do you agree if t is perfect square, 4t is also perfect square, t is an integer?
Yeah.
And do you agree they are equivalent problems?
Yeah.
Okay, and can you tell me why this one is integer? By using what theorem we can say it's integer?
Is an integer like always?
Yes, always. When p is prime, 2 to the p minus 1, or let's say this, 2 to the p minus 1 is 1 mod p always, because p is prime. It is a theorem. Do you know this theorem is what? Name of the theorem?
Is it Fermat's theorem?
Exactly, Little-Fermat's theorem. Little-Fermat's theorem is what? It is this, that if GCD of A and P is 1 and P is prime, then A to the P minus 1 is 1 mod P, right?
Okay.
Okay, memorize this. Have I told you this before? Have you seen this before?
I've seen it before. I don't think you've told me.
Uh-huh. Okay, so one thing that we should work on is Little-Fermat's theorem, then Euler's theorem, and then I tell you order in number theory. Have you heard order?
Yeah, I've heard of it.
And then AIME problem. And for solving that AIME problem, it is so much good for number theory because we will combine all things that we know in number theory in modula, and then it will be so much good. One thing that I should tell you is this one. The other thing, how I told you number of permutations that something is before something, something